All right, it's time. Welcome back. This is our last sort of ordinary class meeting. I hope everybody knows that. On Friday, we're having our test, and then our final exam will be basically our test again. New questions. Here's the date and time for the final exam. It will be in this very classroom on Tuesday at 11:30. So be there. If you want, I suppose. You know, if you feel like your grade is already good enough, then you don't got to come. I want to talk a little bit more about the test at the end, but we do have just one more item on the checklist to get through. In my opinion, it's not it's not really complicated. I wouldn't say it's especially easy or especially hard, but let's just talk about it. By the way, we have homework due tonight. I hope you have checked it out. So what I want to talk about for today, our last thing on the big list, is called the fundamental theorem of calculus. The fundamental theorem of calculus. This is a big and important idea, although it's an idea that we have more or less already talked about, although I didn't say it in very sort of explicit language. I'm going to use some explicit language to describe the fundamental theorem of calculus, which is an idea that has been kind of in the background the past couple times, but let's talk about it for real. So last time, can I just say this is how to find the exact value of one of these guys, the integral from a to b. Remember, this represents the area under the curve of that function. And we have talked at length the past few times about estimating that area using rectangles or trapezoids or Simpsonses. Estimating the area under the curve is something that we've done quite a bit of, but we haven't talked yet about how to actually find the true answer. And that's what the fundamental theorem of calculus is used for. It gives you the true answer to one of those things. Anyway, here is, and like I said, we have almost already talked about this. I just haven't like said it in a very specific way. But last time we talked about the total change, and the thing to know about the total change is if you have one of these definite integrals, but the function inside happens to be a derivative, this is what we were talking about last time. If you're talking about one of these, this is called the definite integral when it's the integral sign with the two little numbers. If the thing inside the integral is actually a derivative, then this is equal to the total change in f of x. Here I'm putting f, not the derivative. So if there's a derivative in here, this area under the curve equals the total change in f of x from x equal a to x equal b. Right? This is what we talked about last time, and maybe even the time before. This is sometimes called the total change theorem. But something else that we talked about a couple times ago, which I haven't really connected the dots exactly, but this is something that we also talked about a couple times ago. The total change from A to B, you can get this total change by adding up all the little bitty changes, which corresponds to adding up the rectangles, or you can just get the total change by subtracting the final value minus the initial value. This is something we talked about maybe 2 times ago. I don't know if you remember. But this total change is also equal to the final value minus the initial value. But you don't have to write that in words. This is just f of b minus f of a, right? Because the two sort of beginning and the end points that I'm talking about are a and b. And so when I say the final value minus the initial value, that's just f of b minus f of a. And so this I'm going to put in a big box, and this is called the fundamental theorem of calculus. Fundamental theorem of calculus, which I will write FTC. And it says the integral sorry, I want to say one more thing. I think we can do it. But something to notice, you will see over here on the left side is a prime, and over here is f without the prime, all right? So the thing inside the integral is the derivative of the thing over here. Another way of writing that, and this is the way that I'm going to write it here, is you could write this one without the prime and write this as the antiderivative. So here's what I'm going to write. I'm going to write it this way. Integral a to b f of x dx. I'm writing that without the prime. And what it equals is, over here, I'm going to use a big F. This is almost always how the fundamental theorem of calculus is written, where the big F is the antiderivative of the little f. I'm going to put that in a box. All right. Just to compare with what I was saying a moment ago. See, what I was saying before had the prime on the inside and then no prime over here. But in any case, it means the thing inside is the derivative of the thing over here. And that's this is also what I'm saying here. I'm just writing this without a prime and saying this is the antiderivative. It's the same thing. All right? This is the fundamental theorem of calculus. And it tells you, remember I said at the very beginning, this is about how to find the exact value of one of these integral things. You can see this, right? This is the integral. And that's the answer. So this is actually very easy to find the value of this. You just have to subtract one thing from another thing. You also have to know what the big F is. So this requires, can I just say, this is easy to do if we know the antiderivative. Like in order to plug into this thing in the box as a formula, if you want to use this as a formula, you have to know what the big F is, which is the antiderivative. But provided that you know the antiderivative, it's very easy. All you got to do is plug in two numbers and subtract them. All right? So we can, but we actually do know how to find the antiderivative of lots of different functions. So this is not going to be so difficult. So let's just do some examples here. How about, everybody's favorite example is this here. The integral from 0 to 1 of x squared dx. Of course, on a graph, what you're talking about is the area under the curve of this parabola from 0 to 1. It's this area here. Look at that, green. I got green on the last day. Bringing out the green. All right. What is this? I'm going to immediately use the fundamental theorem of calculus. This right here equals big F of 1 minus big F of 0. I used the fundamental theorem of calculus. You can still see it at the top there. Now we just have to say what the big F is. The big F is supposed to be the antiderivative of what's inside the integral sign. So here, I'll have to sort of write this off on the side. Big F of x is the antiderivative of x squared. Any antiderivative masters out there? What's the antiderivative of x squared? Yeah? 1/3 x cubed. Yeah. I hope everybody feels good about doing the antiderivative of x squared. So the big F means 1/3 x cubed plus c, of course, and so we can just plug this stuff in. So I go big F of 1. It is 1/3 times 1 cubed plus c. That's big F of 1. And then I go minus. You better put parentheses here because the minus sign needs to distribute across what I'm about to write. Big F of 0 is 1/3 times 0 cubed plus c. All right? And usually you can just kind of leave your answer like that unless you have a calculator, although in this case we can compute pretty easily. This is 1/3, right? 1 cubed is 1, so it says 1/3 plus c minus, and then 0, this part here is all going to be 0. All this is c, so minus c. And the c's cancel, and we just get 1/3, which is the true area, the green area up there is really truly equal to 1/3. All right. this is how we use the fundamental theorem of calculus to find the actual value of one of these area under the curve problems. You will notice the plus c canceled, all right? This is not a coincidence. Actually, in a problem like this, the plus c will always cancel because the plus c is part of the big F. And so in this part, you get a plus c, but in this part, you get a minus c because you're subtracting this part from this part. The c's, if you do it right, the c's will always cancel. And so for that reason, actually, typically people don't even write the c's when you're doing the fundamental theorem of calculus. So the c's, like the plus c's, will always cancel. So we're not even going to bother with them. Although you can put them in there, it's not wrong. It's just they're always, if you do it right, they're always going to go away. So when we do the fundamental theorem of calculus, we omit the plus c's because they are guaranteed to cancel. So you might as well not even do it. All right. Now what I wrote here, I hope you feel like this is a fairly straightforward procedure here. It's a little bit of a pain because I wrote this stuff, but then I had to do this little guy over here and then come back over here. This little sidebar is kind of annoying, just in the sense of how you write this. And so there is a special notation that's used when we're using the fundamental theorem of calculus. We write it like so. There is a special notation. So the way that this is typically written, this is not my own notation, this is how everybody does it. It doesn't make it right just because everybody does it, but in this case, this is how we do it. The integral of x squared dx. Now, it is at this point when you need to use the antiderivative, and here's how we write it. I'm going to write the antiderivative here, and then I put this vertical bar, and then put the 0 and the 1, all right? So this step, you take the antiderivative, and then put the bar. The bar, can I just say one thing? First of all, the bar goes on the right rather than where the integral sign used to be. It goes on the other side. I don't know why. This is just how people write it. So you begin with the integral sign over here. It sort of turns into the antiderivative with this bar. And the bar means, in this case, it's a bar with a 1 and a 0. It means sort of, I'm going to plug in x equals 1 and then x equals 0 and subtract. This is the meaning of that bar notation. All right? This is to make it so that you don't have to sort of separately on the side work out what the antiderivative is. You do the antiderivative right in here. And then the bar means the next step will involve plugging in 1 and then plugging in 0. So I go 1/3 times 1 cubed, subtract 1/3 times 0 cubed, like that. And that's the answer. In this case, you can simplify to 1/3. But this is how we are going to write the definite integral. All right. Let's just try another example, and then I got some for you all. There's no, no big tricks involved. So let's try the integral from 2 to 6, x squared minus x plus 4 dx. All right. If you follow what we just did, there's really just like sort of 2 steps to write. First step, take the antiderivative and put the bar. So I'm going to do antiderivative. We have to go through here and do the antiderivative. X squared gives me a 1/3 x cubed. Remember, the rule here is you should be increasing the exponent by 1 each time and dividing by the exponent. Minus x. This, of course, x means x to the 1, so it turns into x to the 2, and I divide by 2 in the front, so this is minus 1/2 x squared, and then 4. Anybody remember the integral of 4, or the antiderivative of 4? 4x, yeah. Remember, if you have just a constant, the antiderivative of a constant is just that same constant times x. All right, and then I put the bar with the 6 and the 2, and then I guess this will be my final answer. I plug in the 6 first, and then subtract, and then plug in the 2. So we go 1/3 times 6 cubed minus 1/2 times 6 squared plus 4 times 6. That's the whole thing. You go through the whole thing and plug in 6 everywhere for x. And then subtract. Put parentheses because the minus sign needs to distribute. Now you go through the whole thing again and plug the 2 everywhere for x. So I go 1/3 times 2 cubed minus 1/2 times 2 squared plus 4 times 2. And this is the answer. All right? On a test, I would expect you to just leave your answer like that. Although I know there are some people who insist on simplifying. Which is fine. I don't agree with your lifestyle, but I accept it. You don't have to simplify the answers if you don't want to. Okay, anybody got thoughts or questions about that? That's all there is to it. I got some for you all to try. How about, when it comes to the step of doing the antiderivative, you may have to do our usual antiderivative tricks. For instance, root x, you think of as x to the 1/2, and then you do the appropriate antiderivative. I got 4 here. See what you think. I'll try and put the, still see it. Feel free to chat with your friends as always. Yes?
Okay.
You don't need the C's in there.
Right, okay.
Because they, I mean, this is not wrong. Because they canceled the.
Okay, so I could just write it like,
without the C's. Yes.
and put the parentheses on that, okay.
And you don't need to make parentheses.
Oh, brilliant, okay.
Okay?
We're just struggling with it.
Alright? Think so? that.
Yeah, you're
That's
right,
not-
you're right.
1/2 is that.
I was like, I don't know.
You doing okay here? Yeah, that's good. Yeah, at this point you should put the bar. The 4 and the 0.
That was easy. Do you have to put that on the test?
You just don't like it.
No, I'm just excited.
I mean, I guess not, but I don't, why wouldn't you? Maybe like when you did this, you could ask them, like, I have to write that. It's part of the answer, but you eventually writing the answer in, I don't know, you just write it. Doing okay here? Good. This looks good. Good here? Yeah, this you should think of as 4 times x to the -3. Negative 1/3 would be a cube. I like this. And then the next step should be.
Oh, that I have to
4
plug in.
times
Oh,
that.
okay.
Good here? Okay, this one, when you do the integral, it should increase. Because there's always, like in this case, you increase the 2 to 3, and you always get
Oh, that's right. Oh, okay.
Should be good here.
I'm just gonna watch.
All right. It should go very much like, what you see at the top. Doing good here? That looks good.
Yeah.
Oh, can I say this? This is right. I mean, it's good stuff, but that is insane.
No, I got it.
I never actually did it.
So, yes, that's what.
Yes, if this one is equal to. Yeah, this is better.
Okay.
Wait, which one?
Well, it should be the four is a coefficient, so it's just gonna be 4. Yeah.
Yeah.
So it's just 4.
Yes.
It's, yeah, it's 1/3 x. Just
I think this means 9.
So this is a
We have, it's on here, and we have this means 1 over 8.
Oh, yes. I have to.
You good here? Come around once more.
Yeah,
Stay right here.
I think so. At least
This-
this one has like push button.
This thing is.
So you just wrote this. Yeah.
Is it in our list?
But it's in the denominator.
Oh, okay.
So minus.
I got you. Cause you have to bring in like the top.
Yeah. Don't write -3 there.
Cause our hand.
You should write one more step. change the exponent and then divide by the new exponent. Yeah, like if you see the one at the very top there, it said x squared. It really just 1/3 x cubed. What's in front is always 4x over.
Oh, I see.
All right, let's chat about these. I suppose we got plenty of time. So the first one, root x. This one, of course, root x is the same as x to the 1/2, so I'm going to write it like that instead. Notice I still wrote the integral sign here, not the bar. It can be a little bit confusing when you are rewriting the what you started with. I still did not do the antiderivative, so that is just the same as this. Now I'm going to actually do the antiderivative, which means I increase the power. 1/2 increases by 1 and becomes 3/2, and then I have to divide by 3/2 in the front. This is how you do the antiderivative of a power of x. And then I put the bar 0 to 4. 1/3/2, of course, is the same as 2/3. It's the reciprocal of 3/2, so you can write it as 2/3 if you prefer. But anyway, now I'm going to plug in 4, and then subtract, and then plug in 0. So this is, I guess I'll keep it as 1/3/2, and then times 4 to the 3/2 minus 1/3/2 times 0 to the 3/2. And that's my answer. You could simplify if you like. If you really like, you could plug that into your calculator. It is just some number, which represents the area under the curve of something or other. All right? That was the first one. The next one with the e, I think is also, I would say that's an easy one. This one with the e is also an easy one, provided that you remember what the antiderivative of e to the x is. Anybody remember what is the antiderivative of e to the x? It is e to the x, yeah. So this becomes e to the x, and then with the bar 1 and minus 1. It looks like I didn't do anything in that step, but I took the antiderivative because in this specific case, the antiderivative of e to the x is e to the x again. And then you plug the numbers in. So I go e to the 1 minus e to the minus 1, and that's it. That one also I would think of as an easy one, if you remember the antiderivative of e to the x. Any questions about that? Let's try the one with that fraction in there, 4/x cubed. All right, we need to do the antiderivative of this. Can I give you one bad answer first? I saw some people said 4/1/4 x to the 4. Don't do that. Don't play me like that. When you have a fraction like this, you cannot just do the antiderivative inside the denominator. Or if you had stuff on top and on bottom, you cannot just do the antiderivative on the top and also the antiderivative on the bottom. And this is true of a product also. If you have two things multiplied together, you cannot just do the antiderivative of one and the other. You have to somehow rewrite this so that it is in a more convenient form. And in this case, the proper way to rewrite it is using a negative exponent. So this, writing it as a negative exponent, is 4x to the minus 3, right? This is not the antiderivative, that's just the same thing again. Now I'm going to do the antiderivative, which means you change the exponent, you increase the exponent by 1, it becomes x to the negative 2, then you divide by negative 2 in the front. The coefficient, of course, just stays as it is, because that's what you do with coefficients in the antiderivative. Don't also turn the 4 into a 4x. It's not a 4 all by itself. It's a coefficient. All right, and then I put the bar, and now we plug in. So this becomes 4/minus 2 times 7 to the negative 2 minus 4/minus 2 times 1 to the negative 2. I hope you got something like that. Any questions? Thoughts? All right, and the last one. The last one is the hardest, in my opinion, because it has multiplication in there. And I just reminded you a moment ago, when you see things multiplied together inside the integral, you cannot just do the antiderivative of each of the two things. So you may feel a temptation to go, that is 1/3 x cubed, and then this one is 1/2 x squared plus x. You can't do that though. When they are multiplied, if you see multiplication, this is not the way to go about it. Multiplication, remember, is a way that when you see multiplication in there, we often handle it using a U substitution, which is quite a bit more complicated. Although in this case, you don't need the substitution. You can do it by simpler means. Anybody work this one out? What did you do to simplify here? Yeah.
First I distributed.
Yeah, she says, first I distributed. I agree. This is how you should properly handle the product inside of the integral. You should actually do the multiplication for the product. So this, I'm still writing the integral sign because I'm not doing any antiderivative yet. I'm just rewriting the inside. Distributing x squared times x is x cubed, and then plus x squared times 1 is x squared. All right? So that was just rewriting what's inside the integral. And now it looks easy enough. I can just do the antiderivatives and everything will be great. X cubed becomes 1/4 x to the 4 plus x squared becomes 1/3 x cubed, and then the bar, 2 and 3. And we plug in the 3 first. Plug in 3 for x. 1/4, 3 to the 4 plus 1/3 times 3 to the 3, and then subtract, plug in the 2. 1/4 times 2 to the 4 minus 1/3 times 2 to the 3. That's how it goes. All right. I hope you got something like that, and I hope you didn't do something like this over here. All right, excellent. I have just a couple more things to say, and then I think we'll be done forever. A couple more things to say. So, first of all, this fundamental theorem of calculus, we can use this to find true areas, not estimations, but the actual area. So when you see a question like this on the test, I mean, it might just look like one of these, or if they're going to be easier ones like this, I might give you 2 or 3 of these because they only take you a moment to do if you know what you're doing. It might look like that, or it might look like one of those, but just sort of couched in other language. Like I could say something like, find this area, and then maybe have a cute little picture, something like this with a function. How about this function? A parabola like so. How about find this area where this function is f of x equals x squared plus 2. All right? This is a fundamental theorem of calculus problem. I could also say estimate the area using Simpson's rule, something like that. That would be a Simpson's rule problem. But if I just say find the area, and I don't say estimate, I say just tell me the area, then I'm talking about the actual area, which is found by doing the fundamental theorem of calculus. So you need to first, this is not hard, but you need to first set this up as an integral from something to something of something. So I turn this into the integral. It is, the function I'm talking about is x squared plus 2. And I need the 2 numbers, but you can tell from the picture I'm talking about the area from 1 up to 3. So this is this integral, right? And then you just work this out in the same way with fundamental theorem. It's 1/3 x cubed plus 2 becomes 2x, and then evaluating at 3 and 1. So I get 1/3 times 3 cubed plus 2 times 3 minus 1/3 times 1 cubed plus 2 times 1. And this is how I would leave the answer if it was on the test. Right? So sometimes these things can look different. You know, this question was asked in terms of find this area. Or the question could even be in terms of sort of a real world word problem. So here's another one. How about, this is actually the same word problem from last time, maybe, or the time before. I don't remember. Let's say I have my plant that grows. My plant grows at a rate of, given by this function, L prime of t equals t plus 2, let's say inches per week. All right. Now the last time I asked you a question like something like estimate the total change of the length, using Simpson's rule and whatever. But actually, now that you know the fundamental theorem of calculus, you don't have to estimate. You can find the true answer of something like this. So I will say find the total change in length from, say, week 3 to week 5. All right? And I didn't say estimate. Like, actually tell me the total change. And so to do that, you use the fundamental theorem of calculus. The integral, you would set this up as integral from 3 to 5, because I said from week 3 to week 5. And then that function, which is t plus 2 dt, right? I scrolled it. And then we can find the, evaluate this. This is another easy example. T becomes 1/2 t squared plus 2 becomes 2t, and then I plug in 5 and 3. So it's 1/2 times 5 squared plus 2 times 5 minus 1/2 times 3 squared plus 2 times 3. There you go. This is the actual total change. So those word problems about total change, sometimes they will involve estimating using rectangles or trapezoid Simpson. Sometimes they will involve actually evaluating the true answer, which you use the fundamental theorem of calculus for. All right. One thing that it's natural to wonder about, I said in the real world, people use Simpson's rule all the time. Although now you may begin to wonder, if you can do it like this and get the true answer, why would you ever use any of the estimations? This is not even that hard to do. Why would you ever use Simpson's rule? I said people use Simpson's rule all the time. Can't you just use the fundamental theorem of calculus to find the actual answer without estimating anything? The response that I would have is, in the real world, you almost never know the equation for these things. So you could wonder, like last time we were talking about the changing of the Apple stock price. You have to use Simpson's rule to analyze that kind of thing to get estimates. You might ask me, well, why didn't you just use the formula and use the fundamental theorem by taking the antiderivative? The answer is because the Apple stock price does not obey a function that I can take the antiderivative of. It's just a thing that happens in the real world. It doesn't obey some kind of formula. So like the moral of the story is, if you're doing physics, you can use formulas for everything because physics obeys formulas for everything. But in most kind of real world situations, when you're analyzing just something in real life which is changing, you almost never can use a real formula. In that case, you have to do the estimations. All right. And here, I believe, ends the new material for the course. Congratulations for learning everything, or at least being present while others learned everything. What I have to discuss, we have plenty of time left, and I don't think we need to stay here for the rest of the time, but I do have a sheet of practice problems for the test like I gave out last time. These are just the new ones which did not appear on the previous test. If you want more practice for the other ones, go dig out that old review sheet. It's also posted at the class website, so you can go find it again if you are still interested. Like I did last time, I have posted the answers to these ones on the website. And something that will interest everybody, sit down. Something that will interest everybody is, at the very end, on the back of the sheet, it says, formulas I will give you on the test. I felt like there's kind of a lot of stuff to memorize, and so on the front of the test, you will see exactly this little block of formulas. There are other things that you still have to memorize, like the product rule, the quotient rule, and such, but this hopefully will help you out a little bit. I also wanted to say, before everybody leaves, if anybody is interested in your grades, so there are some people whose grades I have been a little concerned about, and I sent out an email to all of those people a few days ago telling you specifically all of your grades so far. So if you didn't get such an email, it means that I am not concerned about you. No offense. But if you would like me to tell you more specifically about your grades, just let me know. I mean, I could do it right now if you like. I also brought some extra of these printed out checklists. If you don't have one, come on and get one. I will expect you, when you come to the test, to know which ones you still have to do. So if you want one of these, I got them. All right, I think that's all. You may stand up again.